appraising and developing stratigraphic traps, the step-out procedure is different. Because seismic data is of little value in these kinds of traps, other available, less accurate data is used to help establish the spill point. Unlike pinpointing the spill point in an anticline trap, finding the spill point in a stratigraphic trap, unfortunately, is less accurate, resulting in a greater potential for drilling dry delineation wells. When looking for the spill point in a stratigraphic trap, it may be necessary to rely on data from outlying, producing fields in the vicinity where data is available. For instance, if stratigraphic traps nearby have shown a southeast-northwest orientation, then the exploration team may use a similar pattern in their own gradual step-out. In any event, once the exact dimensions of the reservoir with its thickness and locations of the hydrocarbon deposits have been determined from an accurate mapping of the OWC points, then OOIP, original oil in place, can be calculated for this subsurface structure. See Chapter 5. Being able to calculate OOIP is important because it allows the team to define and then determine the size and scope of future economic field development. Step-out drilling, therefore, whether in structural traps like anticlines or stratigraphic traps like a pinch-out, is important when conducting a field appraisal for future development. Once the shape, size, and thickness of the contours of the field have been defined utilizing step-out drilling, the next major issue to address is well spacing. Well spacing involves a planned program that determines the optimal number and spacing of wells that need to be drilled to deplete a given reservoir over a reasonable period of time. In fact, it makes better economic sense to produce the oil at a faster rate with additional wells if those wells can produce more than the cost to drill them. How many wells, though, are too many? I'm sure you all remember old pictures from earlier times when derricks dominated the landscape over an oil field. Built practically on top of each other, these wells were drilled so closely together that they quickly exhausted the hydrocarbons' natural lift out of the formation. The result was that in these oil wells, production became so low they had to be abandoned, even though oil was still trapped in the formations. These wells did not have enough lift for the oil to flow to the surface. Good engineering and a better understanding of the reservoir over the years, fortunately, have greatly increased our ability to improve the percentages of the amount of hydrocarbons that can be produced from a given reservoir. Well spacing, therefore, is a strategy that helps improve these percentages of hydrocarbon production while recognizing economic realities. To arrive at an optimal number, assumptions about the future costs of equipment and personnel, the spot and future prices of oil and gas, and interest rates have to be made. In addition, fluid viscosity should also be added to the equation. For most development wells, oil well spacings are typically 40, 80, or 160 acres apart. Remember that there are 247 acres in a kilometer squared. There can be exceptions to how far apart producing wells need to be. Heavy oil fields, for example, could be drilled as tightly as 1/2 acre per well. Gas fields, on the other hand, typically use a 640 acre spacing. In any event, well spacing that defines the number and location of wells to be drilled, along with step-out drilling, are essential components in field development. By knowing the location and the number of wells you will be drilling, you can plan for the costs of the overall equipment, like service facilities, personnel, pipelines, general oil field equipment, etc. being able to put a tentative price tag on the estimated costs of development and production, you are now better able to answer the question of whether you have enough producible hydrocarbons in your field to justify all the upfront and subsequent costs. After the step-out drilled field has been evaluated, optimally spaced wells have been planned, and the decision to go forward has been made based on the field appraisal, the process of drilling production wells to produce hydrocarbons begins. Like all plans, falling production rates in a reservoir over time may force field development plans to be revisited. These wells are known as infill wells. Unlike step-out drilling and well spacing, infill drilling usually is done after the well has been in production for some time, so the equipment to conduct infill drilling will be that of a production well, not an exploration well. There may be several reasons for drilling infill wells. Here we will describe three. One reason to drill infill wells is due to a reevaluation in the time needed to deplete a reservoir. Remember, oil fields are not always homogeneous. For example, some sections of a reservoir may prove to be of lower porosity or permeability that was calculated in the original appraisal. These changes could adversely delay the time that this field could have been adequately depleted using the original spacing. When non-homogeneous conditions arise, these newly drilled infill wells will usually encounter reservoir pressure close to the original values, allowing production to proceed as planned. A second reason for infill drilling is that once primary recovery has been depleted, secondary and tertiary recovery methods may have to be initiated in the field. Secondary and tertiary recovery methods, as we explained in Chapter 5, can require up to 50% more holes than drilled during primary recovery. In these cases, additional wells called injector wells are drilled to add fluid and/or pressure into the formation. Even though injector wells can be either previously drilled producing wells or newly drilled ones, these injector wells can greatly increase the number and reduce the spacing of drilled wells in the field. A third reason for drilling infill wells is to get into places in the reservoir that could not be reached by the original spacing and configuration of the wells. Let's look at an illustration of a field where infill drilling was warranted. This field was originally drilled in an 80-acre grid pattern. To infill, a well is drilled in the middle of each square with the 4 original wells forming the corners. In effect, these center wells can double the number of wells and change the spacing in this field from an 80-acre well spacing to a 40-acre spacing. Although step-out well spacing and infill drilling are common in both onshore and offshore fields, it should be pointed out here that due to lower costs, onshore appraisal and development enjoy at least one advantage. Because adding additional production onshore facilities is relatively cheap in comparison to offshore, onshore development is better able to proceed in what is known as a phased development of a field. Phased development, a popular choice, allows both appraisal and development activities to occur simultaneously so that costly errors can be more readily remedied. Offshore appraisal and development does not have as much margin for error. For example, the appraisal process, even for oil, is much more intensive in very deep water. There, it is necessary to make certain that the field size and production rate will be high enough to justify the enormous upfront costs of the platform. This is a very different economic profile than that for onshore or for shallow water development, where each well can stand alone and be profitable in its own right. Offshore, the field in deep water must be large enough to justify the added costs to develop it. Once all the available data has been evaluated in a field appraisal, a final decision will be made that determines the next step. If hydrocarbons are present in economic quantities, and if they can cover the costs of the development, and if economic conditions are right, the company will most likely develop the field. Onshore, many times the wildcat well, as well as some of the delineation wells drilled during step-out drilling, can quickly and easily be readied for production. In addition, portable jackknife land rigs can be pulled by trailers to the site on newly constructed or existing roads to complete the drilling plan as outlined in the appraisal. As you might guess, in very shallow, protected offshore fields, development may proceed similarly to those onshore. The deeper the water and the increasing intensity of the wind and waves sitting on top of the field, however, present additional challenges that usually increase costs and the time required to get the field into production. Let's examine the equipment and procedures used to address these challenges in developing a field offshore. We'll begin with the most protected of offshore locations. In shallow, protected waters found in marshes and estuaries near land, production procedures are very similar to those found onshore. Here, barge-mounted rigs are easily pushed to location where the barge is then flooded until it sits on the bottom. Once a vertical well is drilled and completed, the barge is then refloated and moved to the next location, leaving the wellhead and Christmas tree sticking up out of the water. For very shallow water depths of less than 10 feet, dredges are used to cut access canals for the drilling barges. A work barge is moved in and a small jacket or toadstool is set down over the tree and pinned to the bottom with piles driven through its legs. This functions as a dock for small boats used by the operating personnel and gives them a place to stand while working on the tree. This jacket or toadstool also protects the wellhead from being accidentally struck by other floating barges, boats, or debris. Barge-mounted rigs are ideal for areas where water depth does not exceed 25 feet. Not only can barges be used in shallow water, they can also be used onshore in low-lying swampy areas.